All right, hello everyone. Welcome to our next unit, and this one has to do with apportionment. The most common thing that you're going to see here is apportionment of the U.S. House of Representatives. Um, Apportionment refers to any situation in which we have resources that we need to allocate, or we have like seats that we need to fill with like representatives. Um, what we're trying to do is we're trying to create either representative groups, or we're trying to split up resources according to some ratios using some data that we know about our population. Now, that may not seem like a terribly hard problem to do, but there are some issues that do arise with this. Um, so our goal here is to learn several methods for creating these sorts of representative bodies. Um, you might be thinking to yourself, like if you're thinking about, say, the House, um, well, don't you just divide it up by population? Like, so, say California has 12% of the population of the United States, so they should have 12% of the representatives. Yes, that's absolutely true. But what's going to happen is it's actually tougher in theory, or easy in theory, but tougher to put into practice. And the reason has to do with how to deal with partial seats. Um, as we know, politicians can be very vocal about their opinions, and they're going to try to fight for every last thing that they deserve. So what winds up happening is the politicians in the past have kind of fought over how to handle some of these seats in cases where you have like not an even number. And we're going to see situations like that come up. So let's get right into it and kind of see how this all comes about. Okay, so let's start off really, really simple. Let's say we're going to create a 20 student council group. Um, we want it to best represent the student population. So let's say that the best way that we can do that is by matching male and female proportions. So we have 20 students, right? And we know that 55% of the students are female, 45% of the male. So how should that translate to a 20 student council? Well, if you think about it, this isn't probably all that hard. We would want to know what 55% of 20 is, because we would want 55% of this group to be female. And it turns out that's exactly 11 female, and therefore there should be 9 male. And that happens to be 45% of 20. And that's pretty easy enough to understand there. Remember that in order to deal with proportions, the easiest way to calculate it, if you ever need a calculator to do anything, is 0.45 times 20, and that will be equal to 9. Okay, now that works out nicely, but as you can imagine, not every group works out nice and even. Let's say instead we go by class, freshmen, sophomores, juniors, seniors. And we would also like a council of 30 instead of a council of 20. Well, now we have some percentages that aren't quite exact. So when I try to use this and apply this, I would have to do 0.28 times 30, which it turns out is 8.4. These here, 25% of 30, these would be 7.5% each, or 7.5 and 7.5. The seniors, 22% of 30 is 6.6. So what winds up happening in this case is we get decimals. Okay, now some of them you might say, well, all right, well, what's the easiest thing? If you want as close a representation to the true value as possible, you just round to the nearest integer. Okay, great, let's try that here. If we try that here, well, let's see. 8.4 would round to 8. 6.6 would round to 7. 7.5 and 7.5, well, those round to both 8 because they round up. And 8 plus 8 plus 8 plus 7, well, that's 31. Now, I know what you might be thinking here. You're probably going to look at this group of the sophomores and juniors, and you probably realized already that if there's 8 and 7 freshmen and seniors, there should be 8 and 7 sophomores. Okay, well then, hot shot. Which one should be the 8? Which one should be the 7? Yeah, see how tough of a decision that is? This is the problem that um, can happen a lot with these sorts of apportionments, is that when we try to round to the nearest whole number, um, we do end up with situations where the numbers just don't quite work out. In this case, we end up with a 31 instead of a council of 30. If we apply the same traditional rounding rules that we all learned in elementary school. Okay, so you might be saying, well, what's the problem? Just have 31 people. Well, that doesn't always work. Okay, here's here's the thing. The US House of Representatives has 435 people in it. Okay, oops. All right, so let's go here. The US House of Representatives has 435 people in it. The thing with this is that that number was set by law in 1911. So let's go back a bit here, go back to this page. So the House, 435, that was set in law in 1911. And that can't change. Now think about it. It can't go up because there's no more space. The reason why that number was set is there's no more space in the House chamber literally at all. Um, it is possible in a pinch to add a few more. We'll talk about that in a second. But generally, that number can't go up. It can't go down because it would be political suicide for any representative to actually want to lower the representation. So that's not ever going to fly. Not unless they could get everybody to agree to lower, and that's not going to happen. So 435 is going to be where it's stuck. Not going to go up, not going to go down. And so we're not going to leave open seats, and we're not going to suddenly add seats. Again, if anybody suddenly adds a seat where they're not due, you're going to have a lot of squawking people. Both representatives and the public that's clued into this sort of thing, right? So this cannot change. So we end up with these numbers here. So we know that one of these has to be 8, one of these has to be a 7. But which is it? This is the problem that we're up against. Okay. Let's look at another example of that. So here's, again, just going by what we said before, selecting a different council size is not an acceptable resolution because especially when you're talking about Congress, we do not have the power to change that number. Okay, this is also true in the case of resources as well. Suppose we need to allocate resources. Let's say, for example, we had, I don't know, 55 pallets of supplies. Let's say we try to give them to like hurricane damaged areas, say in the Caribbean, right? There's an island that needs our help, and we're going to bring them 55 pallets of supplies. But we want to apportion it out to different areas on the island. Well, if we do the math and we come up that we need 56 pallets of supplies, we can't just magically make a new pallet appear. We're also not going to let pallets go unused either. So therefore, we're stuck with this number. So in any situation that we have this size that we get is what we have to deal with. Okay. So here's a good example of that. Canada, Mexico, and the US want to send 400 business leaders to a conference to discuss future NAFTA treaties. So in millions, here's the population. These are correct as of maybe 2012. Um, the total population is 461, and that's in terms of millions. Now, what we may want to do is we want to convert this into some group out of 400 leaders. So we want to use these to try to figure out how to convert this into a proportion out of 400. So again, let's do the same thing that we did before. Um, so this time though, how do we look at this in terms of a percentage when we're not given the percentages? Well, to find Canada's percentage, right? We want to create that as a ratio out of the total. So 34 out of 461. But then, because that's the ratio and that's as a percentage or a decimal, we're going to take that and we're going to multiply that by the 400 liters that we have available. And we're going to get a number for that. And that number is, let's do the math on that. So do this. And I'm opening up a calculator. I don't know if you can see this on my screen. 34 divided by 461 equals about 7.37%. And we're going to multiply that by 400, 29.5011. Okay, now one thing you're going to notice about this, and I'm going to be very consistent here, 4 decimal places. So you're going to notice that I do this to 4 decimal places. The reason for it is so that the first 3 decimal places are all accurate. We can round the 4th decimal place however we wish, up at 0.5, down at 0.5, that's fine. But we want the first 3 places. The math that we're going to do in this unit, this sort of like ratio math, and we're going to have several sorts of successive calculations to do on this data. And we're going to be creating several columns as we go along. That means that any rounding errors that happen now will compound themselves further and further and further the more that we do this. So you have to keep these numbers as accurate as possible for as long as possible. In my experience, I've never had a problem using 4 decimal places. With 2 or even sometimes 3 decimal places, if we start with like 2 or 3 at the beginning, those errors can compound enough that by the end of a lengthy problem, we're actually off by whole numbers of seats. It is entirely possible for that to happen. So let's keep 4 decimal places. All right, let's go back and let's finish out the rest of these, right? So we're going to do the same thing with Mexico, and we're going to do, was it 114 divided by 461 times 400, and I get 98.9154. And then for the USA, 313 divided by 461 times 400, and I get 271.5835. Okay. All right, so now my question again, just like before, is how many, based on these decimals, how many people should we really send? Okay, so these values here represent the exact number of representatives as the exact proportion out of 400 that this population would dictate. So that means that I should send 29.5 representatives. Well, can't send 29.5, right? So let's call this 30. What about Mexico? 98.91. Well, that's almost 99. Let's send 99. That's very close. 271.5835 for the USA. Let's send 272. And when I add that up, I get, oh no, 401. So remember what I said. In situations like this, just sending the 401 is not a good idea. Um, we do not have that capability. We don't have a seat for them. And if this were resources, we don't have that extra resource. So guess what? Something's got to go. Who's going to give it up? Which of these countries should give it up? Okay, so what's your first thought? Well, it looks like Canada. Canada has 0.5011. So they have, even though it's above zero point 0.5, they have a smaller decimal than the others, right? So they have the least amount needed towards an extra representative. So therefore, if these people don't get one, because they were the farthest away from needing the extra representative, um, we can do that. And so that would be 29. So what we could do is we could cross this out with 29, and then now here, 400, right? Okay, seems legit, right? I mean, Mexico 0.91, so they practically have a need for a 99th representative. That's good. And then USA, not quite, but certainly more than a bigger decimal than Canada, so that makes sense. Okay, do you see any reason why someone else should lose a seat instead of Canada? Well, notice that Canada was by far the smallest anyway, and it was by far the smallest represented. Yes, it has a small population, but the smallest represented, and they ended up losing one. Is that very fair? Like, if Canada loses one, they've lost 3% of their representation. USA, if USA instead loses one, right? So let's go over here. Let's say, for our purposes, let's say USA loses one instead because they were so much bigger than everybody else. Now this is 400 again. Is this really going to change anything? No, probably not. So you could make the case that maybe it's the USA should lose one simply because they were so far above everybody else that losing a representative does them really no harm. So you might start to see how different opinions might lead to different results. And this is where our unit comes into play, and this is why we're going to study apportionment, because these opinions have shaped how we allocate resources in many areas. Okay, so a little bit of vocab for you. Most of the time, we're going to deal with this from the political perspective. So seats, house size, states, population, total population. And when we're talking about legislative bodies, these will be the very literal things. So seats will be seats. House size is like the size of the House of Representatives. So all of that will be true. Where the vocab will start to differ is when we deal with non-political problems, and we'll do an example of that in just a bit. But first, let's learn our very first explicit method of apportionment. Okay, so in the case of the US House, the House size is 435, right? The total population of the US, according to the 2010 census, is 309,183,463. That's one representative for every 710,766.6 people. Again, very precise because I don't want to cause errors to compound. This number, this represents the number of people necessary to earn a representative. This is called the natural divisor. Whenever we build this out, it's in terms of the unit of measurement is in terms of population per resource unit. And in this case, the resource unit is a representative, but it could literally be anything. It could be pallets of food. It could be, as you'll see, other objects that we want to allocate. To figure out how many seats should go in each state, divide that state's population by the natural divisor. So the state's population divided by natural divisor. So here's the thing, like for Connecticut, Connecticut has a population of about 3,600,000 people. That's the state's population. If you were to divide that by, what was that, about 710,766, you're going to end up with a number about 5.06 representatives. That means that Connecticut gets 5 representatives. We've earned 5. Plus, we have 0.06 towards another representative. Not enough in our system for another one. That's an easy one to round down. Just like how the Mexico problem earlier got rounded up because it was such a high decimal, Connecticut's value in most cases will round down to 5. Okay, so what we're going to do is we're going to have to do this population for each and every state. Good news is you're never going to do this for all 51 entities in the United States of America. That's just not going to happen. And yes, I said 51 and not 50, and that's because in terms of the Electoral College, District of Columbia does have a say in that, and so they are apportioned for that one instance. They do have a slightly different apportionment. But anyway, the regular true apportionment of the 435 people, we're never going to do all that for all 50 states. We might do that for, say, the original 13 colonies would be an interesting situation, but never on the full thing. But somebody has to, right? And that somebody, you'll see in a bit. United States Constitution, Article 1, Section 2. Holy crow, I'm actually pulling out the US Constitution here. Imagine that. Wow. Yeah, this is the legitimate text from it too. With highlighted parts are important here. So here's what the Constitution has to say about apportionment. Representatives and direct taxes shall be apportioned among the several states according to their respective numbers. We take that to mean population. But why didn't they just say population? Because population back then was kind of a varying term. You had slaves, you had Native Americans, you had other people that only kind of partially counted. And they also specifically left this open in case there was some reason why they didn't want to base it on direct population. So they left that kind of open like that, and they did that on purpose. The actual enumeration shall be made within 3 years after the first meeting of Congress of the United States. That was done, 1790. So that happened, 1790. And within every subsequent term of 10 years, that's the census, we do that in such manner as they by shall want direct. So Congress sets the rules on that. Number of representatives shall not exceed 1 for every 30,000. And each state shall have at least 1 representative. Okay, cool. So what does this mean? This means we cannot have more representatives than we have for every 30,000 people. So That means in something like the state, let's look at the whole country, right? So 1 in 30,000. Well, if we take 310 million and divide by 30,000, that would be a representative of about 10,300 plus representatives. I'm not going to do the exact math on that, but it's over 10,300 representatives. We don't have anywhere close to that. We have 435. But back in the early part of the country, back when, 30,000 people was a lot, and like there were some states that had that population. Um, because everybody was so spread out, having one representative for 30,000 people um, was considered an appropriate amount. But very quickly, that number grew. And as soon as it did, within 20 years after the Constitution, this section of 1 for every 30,000 became an absolute moot point. Okay. But each state shall have at least one representative. So this part's important. If a United States is a state, it automatically gets a representative no matter what. No matter what the division says, no matter what the decimal says. Okay. So the question is, who came up with all this stuff? Well, our friend Alexander Hamilton. As we saw before, simply dividing and rounding is not dependable to create an accurate apportionment. So Alexander Hamilton, who is credited with doing so much in the early days, he's Secretary of Treasury in 1791, underneath George Washington, and during his first term. So he creates a way to apportion this because he realizes that somebody has to create this. Congress is going to have to approve it, but somebody has to write it, and so he decided to take this on. And his idea for apportionment eventually is liked and becomes the Apportionment Bill of 1792. And this is what it says. Number 1, calculate the natural quota for each state. That's that number that says the exact with the decimals of how many representatives that state gets. Round each state's quota down to the nearest whole number, regardless of what the decimal says. Basically, what you're going to do here is this is like truncating. We call this truncating. In other words, what we're doing is we're assigning the whole number of representatives that get awarded first, though, because those will not change. So when Connecticut was 5.06, we allocated 5. We've earned those 5 representatives. Same thing with Mexico. Mexico had 98.91. We allocate the first 98 of them because those they've absolutely earned. They have a full group of representation. Eventually they'll earn the last one, but we'll get to that. Allocate first. Step 3. If there are seats left to assign, and in this method there will be, assign them to the states with the largest fractional parts until all have been assigned. Isn't that what we just did before? Hamilton's method was not groundbreaking. It was very common sense. Just give the extra seats to the states with the closest to go to earning it. That way everybody is as close as possible. That makes sense. Let's do this with fire trucks. So suppose we need to allocate 21 fire trucks to 5 stations in a city. So again, we're going to do this in a very non-political way just to see how this works out. We're going to do so based on the reported number of fires over the last 3 years. So instead of a population of people, we're going to have a population of fires. And what I want to do is I want to assign the fire trucks, the 21 fire trucks that match these ratios and proportions as best as possible, such that the total is exactly 21. So you can see how this can be a tricky problem now that you kind of look at it at its entirety. We have to find the group that matches the proportions given here as best as possible while still equaling 21 fire trucks. So how does that work? Well, let's do some calculations. The first thing that you're going to need, okay, is you're going to need the total. The total is 686, right? So to calculate a natural quota, okay, and I know I have it all written down here already, but that kind of saves it a little bit of time here. So here's what you're going to do. For each of these states, you are going to take the number of fires, okay, and the very first thing is you are going to create a divisor. That's what you're going to divide this by. So the divisor is equal to 686 divided by 21, and that's going to be population per truck. Or in this case, more appropriately, fires per truck. So in other words, how many fires does it take to earn a fire truck? And that number in this particular case is 32.6667. That's a very important number. And again, keep it to 4 decimal places. And you know what? I don't care if you know that it's 0.6 repeating, or that it's like 32 and 2/3. You need to use 4 decimal places. And the reason is if you don't write them down explicitly, it can be very easy to forget that you do have to work with 4 decimal places. In this case, consider using those sorts of shortcuts like fractions or repeated bars. They're shortcuts and they're not going to give us the most accurate answers. Now, if you want the absolute most accurate answer, use the fraction instead. But I digress. Okay, so what you're going to do is you're going to take each of these numbers, the 154, divided by 32.6667. And that will get you this number here. Okay, so 154 divided by 32.6667. Okay, and that gets you 4.7143. Okay, do the same for the others. 83 divided by 32.6667. 129 divided by the number. 217 divided by that number. Okay. The next thing you're going to do, and for this, I'll just kind of write this out again, just so that this is nice and clear. Okay. So what you're going to do is you're going to then allocate all your initial fire trucks. So how many do I get? Well, this group's earned 4. This group has earned 2, 3, 6, and 3, regardless of the decimals. Even this decimal 0.9490, they have earned 3, and only 3. Okay. Now, if we look at the numbers, that's 18. They have assigned exactly 18 of the fire trucks. 6, 6, and 6. That means we got 3 left. We have 3 fire trucks left. Who's going to get them? According to Alexander Hamilton, highest decimals. And so those highest decimals, so station number 3 is the closest to earning a fire truck, so they will get 1 extra fire truck. Mark it off with like a little plus sign. You can do a check mark or +1, however you want to do it. What's next? 0.7143 plus, and then finally 6.6429 plus. Those three stations have earned an extra fire truck. Now, the nice part about this is you will never assign multiple extra fire trucks or resources to the same place. With this method, you will never see that happening. So we will round this to 5, 2, 4, 7, and 3. This is your final allocation of fire trucks. 5 to station 1, 2 to station 2, 4 to station 3, 7 to station 4, 3 to station 5. Okay. And the total adds up to now exactly 21. All the fire trucks have been handed out. Okay. This is Hamilton's method, and this is in use in many, many, many places around the world in terms of how they run their governments. We actually do not use this method here anymore, but we'll get to that and how that method changes over the course of time. So I'm going to leave this here without making the video too long. This was a nice introduction to Hamilton's method, and just kind of going over the notes and how it all works. Okay, I will see you later. Have fun.